All right, so we've been working our way up from beginning of the semester looking at the smallest particles that make up atoms, and that helps us understand how atoms behave. We got a sense for the noble gases being so stable and other elements wanting to arrange their electrons around them so they have the same number as a noble gas. That is the main factor that determines how atoms bond together and why they bond together. Now, so far we've been dealing mostly with pure substances, where if I just have all of my units having the same element, or maybe I bond the elements together to make a molecule, and every unit is made up of the same molecule, then that would maybe be a solid or a liquid or gas, depending on the intermolecular attractions. But what happens when you mix a substance with another substance? So one molecule and another molecule that's made differently with different elements or bonded in a different arrangement. When you do that, there's a couple things that can happen. It depends on the stability of the substances you're adding. So if the substances you're adding are relatively stable, how do we judge stability of a substance? We look at the electron arrangement to try to see if they have noble gas configurations, and if they're no formal charge, maybe there's resonance, helps to stabilize it. And so we talked about ways that molecules can be arranging their electrons to make them stable versus unstable. So if they're relatively stable, nothing will happen. They'll just occupy the same container. They'll just be together. And when they come together and they just mix together, there's two ways they can mix: homogeneously or heterogeneously. We already talked about that. The substances will mix homogeneously if they can form similar attractions to one another that they form when they're not mixed, which we'll talk about a little bit more later in the semester. If they form heterogeneous mixtures, that's usually because one substance can really form strong attractions with other molecules of the same type. And so the substance I want to mix in with that won't come in and break up those attractions, like oil and water. If I put oil on water, it just kind of sits there and floats on top. That's because the water molecules can hydrogen bond. One water molecule has a big partial negative on one end, big partial positive, because of the big electronegativity difference. So the water molecules line up and form big, strong dipole-dipoles, or hydrogen bonds in that case. The oil molecules are nonpolar, so they only form temporary weak partial charges, so they can't come in and break up the attractions between the waters very effectively. So when substances don't mix and they form heterogeneous mixtures, it's not because they repel. It's not correct to say that water repels oil. It's just that the attractions water makes with oil are not nearly as strong as the attractions water makes with water, so the waters just stick together with their own kind. We'll talk about that a lot more in detail, but what we want to talk about in this next section is what happens if the substances I'm mixing together are relatively unstable. Maybe one of my substances doesn't have a complete octet, or maybe it has a formal charge that makes it a little bit unstable. Or maybe it looks totally stable, but if substance A, with its electrons arranged around it in a certain way with certain bonds, if that could come in contact with substance B, maybe everything's perfectly stable. But maybe when they mix together, there's just a slightly more stable way to arrange the electrons and the atoms together. So maybe if B comes in here and joins in, maybe then it's just slightly more stable. If that is the case, then I will get a chemical reaction. I will get some change in the arrangement of the electrons. A new bond forming, maybe an old bond breaking. Maybe the electrons just hop from one atom to another. So some change in the arrangement of the electrons is what defines a chemical change. And that will usually occur if that new arrangement, upon changing the arrangement of the electrons, produces something that's more stable. So if it's somewhat unstable, maybe maybe it has an incomplete octet. That would make it very unstable. Or a lot of unstable formal charge or charge repulsion. That would make it unstable. Maybe it's mostly stable, but it only has some loosely held outer electrons. You know, if I have, in the example we did in lab 3 with the halogens, you know, chlorine maybe that only has 7 electrons, and an iodine that has 8. Well, the iodine's electron was more loosely held. So if one is more loosely held, it's susceptible to undergoing a change in the arrangement of its electrons. Maybe another atom will pull an electron off of it. Right, so any change in the arrangement of the electrons is considered a chemical change, and usually that change will occur because the new arrangement that results after the change allows the electrons to be more stable, closer to a nucleus, pulled in tighter, and make stronger attractions in one way or another. So in order for that to happen, though, we need to provide the means for the substances to collide. They can't just be in the same container. Otherwise, the process can be really, really slow. Like the process where a diamond gets converted into graphite. That process is happening. So if you own any diamond jewelry, someday that diamond will not exist anymore. It will be in the form of graphite. That's not going to happen for thousands of years because the process is really slow. Because the process does not provide for frequent collisions between the atoms, and collisions are necessary for the rearrangement of electrons. So if you're going to change how the atoms are arranged and how the electrons are arranged around them, you first have to start by overcoming any initial attractions that are there for the electrons in their initial arrangement. That requires a collision to break some of those attractions so that they can rearrange in a new way. So to facilitate that, if we want that to happen intentionally, we want a chemical reaction to occur so we can create something new, something useful with new properties that has a different arrangement of electrons. We need some temperature, because temperature means motion. We need things moving faster so that when they collide with force. It provides forceful collisions. We also need a medium to allow them to flow and collide with force and to allow them to meet up often. And the best medium for that is a liquid or a liquid solution. So gases are nice because particles move fast, right? When a particle's in a gas, it's flying around quickly, it collides hard. But the problem with gases is that in gases, most of the molecules are not very close together. So the collisions just don't occur very often. In a liquid, everything's close. Things are close because there's some intermolecular attractions, but it still has flow. So in a liquid, things can flow around, move around, and collide, and usually they're close enough where they can collide often. So if I want to set up a chemical reaction, usually I do that in a solution. I take a solvent, maybe like water, and I dissolve in that solvent one reactant and another reactant, and the water facilitates their collisions, allows the electrons to be rearranged to produce a new product. So when I'm working with solutions and I want to be able to create a new substance, I also want to be able to consider both the substances and the energy that's involved, which we'll do a little bit later in the semester. But I want to be able to do that qualitatively and quantitatively. I want to know, what substances do I have? What substances am I going to make? Does that process require me to put energy in, or is energy going to be released? And also, quantitatively, how much? How much product can I make? How much energy is going to be associated with the process? Right, so that's what we're going to be looking at here for the next few weeks. So, as we said, solutions are the best usually for facilitating chemical reactions or rearrangements of electrons. So we want to understand quantitatively how to deal with solutions. So in a solution, you've got a solvent. That's the main component of the solution. You've got a lot of that, and it's usually not, sometimes it is, but it's usually not one of your reactants. It just facilitates the collisions. So I've got this liquid here. It's my solvent, and I'm going to add to it my solute. The solute is what I'm dissolving in the solution. Those are usually my reactants. So depending on how much space those reactants have to spread out in, whatever the solute is, maybe it's just some molecule, I'll just represent that with a sphere. If I put only a little bit in, am I going to be able to have a lot of reactions occurring in a given period of time? Probably not, because the reaction requires that the solute molecules collide. So if I want more collisions, I need a higher concentration, or I need more molecules in a given amount of space. And so concentration is usually measured in molarity. There are some other concentration units we're going to see, but molarity is usually used because it's the moles of solute, which is the number of particles. A mole is just a number of particles. The number of particles dissolved in a given amount of space. The greater the molarity, the more closely packed the molecules are that I'm dissolving. Right? So this is at a higher concentration or greater molarity, and this is at a lesser molarity. The particles are not as close. If the particles happen to absorb light, I don't know why this won't turn off here. Really weird. I can dim it. Okay, that works. See that better. If the particles absorb light, then they will be colored, and I can tell by how light the color is or how dark the color is, at least qualitatively, which solution is more concentrated. So that's useful as a visual. But many substances are colorless, so I can't tell by looking at it which has a higher concentration. I need to be able to calculate that. So we want to do some practice calculations here, looking at solutions. Actually, before we do that, let's look at one of these simulations here. Let's look at this one. So here, I'm not going to add drink mix. I'm going to add an actual substance here. So I'm going to go with the green nickel chloride. So nickel is a metal. When it forms an ionic compound with chloride ions, it absorbs visible light in the region, in the red region. So if it absorbs red light, that red light gets pulled in and converted to potential energy by the nickel atom. It's green to your eyes because when the red light is absorbed, that red light's not reflected into your eyes anymore. The other colors, like green, are reflected into your eyes, so that's the way your eyes interpret that. So if I add some of that nickel chloride, I just add it to the solution looks green, right? So I can measure the concentration, 0.920 moles per liter. Right? That means if I had a liter of solution, which I don't, I only have half a liter, but if I had a liter, I would have 0.920 moles. That's a specific number of individual nickel atoms and chloride ions. Right? So mostly that's water. I just added a little bit. It's a homogeneous solution because the nickel dissolves thoroughly. And I get an even green color throughout at a medium shade of green because I have a significant number of nickel ions and they're absorbing light. So what will happen to the concentration if I add more nickel? Yeah, it'll go up. So if I add more, it gets a little bit darker, the concentration goes up. Right? The more moles I put into a given amount of volume, the greater the concentration. What will happen if I evaporate some of the water? What will happen to the concentration? If I evaporate, so the nickel has a charge. It's a 2+ charge, and the chloride has a negative charge. So the attractions between the nickel and the chloride are very strong. So if I allow that to evaporate, those are not going to be evaporating. But since most of this is still water, and the water is only held by relatively weak in comparison hydrogen bonds, that I can break. So if I allow the water to evaporate, only the water molecules are going to be leaving. If only the water leaves, the volume will go down, but I still have the same amount of nickel. So if I evaporate it, the concentration will go up. Because as I have less water, the nickel that's present is now present in less and less space, so it gets darker and darker because now the nickel is more concentrated. The nickel atoms that are present are closer to one another. So I would have a much higher concentration then. What if I then dilute it by adding more water? What will happen to the concentration then? Then it will go down, right? So if I add a bunch of water in, take it up to a liter, whatever, now it's much more dilute. What if I add, instead of adding solid nickel, I add a solution of nickel? Well, as long as my initial solution is more concentrated than what I'm adding it to, it'll continue to get concentrated. What if I dump all this out and just add this? Well, then the solution I create is the same concentration as what I'm adding. Right, so you can get a sense for, if that's 5 molar in here, this concentration in here is 5 molar. I dump it all out, just add a little water. What will the, a little past where I wanted to go, right there. So let's say I have half a liter of water. I'm going to add this 5 molar concentrated nickel to that until the total is 1 liter. What will the concentration be? Yeah, it should be 2.5, right. So just conceptually, if half of it is water and half of it is this concentrated solution, that water should be diluting the concentrated solution to the point where it's half of what its initial concentration was. So you can get a sense for how this works. You have an idea of how it works. So let's do some more detailed calculations related to this. So let's say I wanted to dissolve glucose in water. I want to determine the molarity, right? So this is something you might want to do. You can do it on paper. If you don't have the means to measure it, you can calculate it if you know how much of the solute you're adding and what the total volume of the solution is, because molarity is moles of solute, which in this case is the glucose, divided by liters of solution. That's what molarity is. So if I have 50 grams of glucose and I dissolve that in 2 liters of solution, that's almost molarity. Instead of moles per liter, I've got grams per liter. So what do I need to do to get to molarity? Right, I need the molar mass. So I would add up 6 carbons, 12 hydrogens, 6 oxygens to get the molar mass. 12.01 times 6 plus 12 times 1.008 plus 6 times 16, and I get 180.156 grams of glucose per mole of glucose. Right, so this is, I really would think that it will really benefit you if when you're doing your conversions, don't just put grams per mole. Include the substance that you're dealing with, because I've got multiple things here now. Once I start to mix things together, I might have a reaction where I've got glucose and an acid, or like multiple things reacting. At the very least, I have glucose and water and solution. A gram of solution is not the same as a gram of glucose, because in the solution, only part of that mass is mass of glucose. So it's really very helpful to keep track of what substance you have, because I want moles of this substance per liter of the total solution. I don't want moles of water per liter of solution or moles of glucose per liter of glucose. I want specifically, for molarity, moles of solute per liter of solution. So I need to plug things in a way that makes sure I get to those units. So I've got moles of solute per liter of solution. Then I know I've plugged things in right. So I can do 50 divided by 2 divided by 180.156 0.156, and I get 3 sig figs, so 0.139 molarity. So the symbol for molarity is a capital M. And you can also write molarity as moles per liter. That's the same exact thing. Questions about that? Okay, so I've got this solution. What do I see? Well, molarity is 1 unit per another unit. That's a relationship. So if I have this solution at this concentration with this molarity, I can use that as a relationship to solve problems like problem B, which is if I want to know the volume of the solution, if I wanted it to contain 0.250 moles, I can use this as a relationship between moles and volume. So if I want to know what's the volume or how many liters of solution do I need to make 0.250 moles of glucose. This is a conversion. I want to convert this quantity from one unit to another. I need a relationship. That's what molarity gives me. So the relationship is 0.139 moles of glucose equals 1 liter of solution. So I can cancel the moles of glucose and I can get the units I want. So 0.250 divided by 0.139, it gives me 1.80 liters. That's really helpful. I mean, this is really practical stuff. If you're doing any laboratory work or medical work where you're working with solutions of drugs or whatever, you're probably going to have to work on some types of conversions like these, because when you buy a chemical or buy a drug or something, if you're a pharmacist or whatever, it's going to come in some concentration most likely. Probably not going to come as a pure substance. If it comes as a pure substance, you have pure glucose, and you just measure out how many grams, convert that to moles, and put it in some volume of water, and you know the molarity. But if it comes as a solution, it will tell you what the initial molarity is. You have to use that as a relationship. So if you know, well, I want to give this patient so many grams of medication or so many moles of medication, or I want to do this chemical reaction and I want to supply enough of one reactant to fully react the other reactant, I need to know how much of this solution to put in. So this is the type of problem, this is the type of solution that you use to answer that question. So if you want to provide a certain number of moles, a certain quantity of a drug or a reactant to a chemical reaction, and it's in solution, you divide the moles. You use this as a relationship to calculate, I need to add 1.8 liters of this solution if I wanted to supply, at that concentration, I want to supply 0.250 moles. You might also want to answer a slightly different question from a slightly different point of view, which would be like C. C says, if I have a certain volume, how many moles is that going to supply? So in this case, I use the same relationship. I just flip it because I want the liters to cancel this in this case. So I would do 0.139 moles per 1 liter. That's moles of glucose per liter of solution. So the liters cancel. Got the unit I want. 0.5 times 0.139, 0.0695 moles of glucose. So if I did add half a liter, that's how much glucose would be in it. Any questions about that? Okay, so a lot of times you might also need to do a dilution. This is very common because if you buy a chemical, usually comes very concentrated. Right? If you're a company and you're selling chemicals, do you want to sell diluted solutions to people or concentrated solutions to people? Well, if you sell a diluted solution, if you sell a liter of diluted solution, you're not giving them much of the actual substance. You're giving them mostly solvent that the substance is dissolved in. So if you want to buy 12 grams of hydrochloric acid from me, and I give it to you very diluted, I might have to give you 8 liters. That's going to be a pain to ship. If I give it to you concentrated, then I can supply that 8 grams to you in a much smaller volume, and so it's much easier to ship. So when you buy things, they'll either come pure or they'll come usually in concentrated solutions. But sometimes you don't want the solution to be concentrated when you're running a chemical reaction, especially in medicine and pharmacy. You don't want a drug to be too concentrated because you don't want someone to overdose. You don't want them to get too much. So you need to do dilutions. Dilutions are a situation where you take a certain amount of a concentrated solution and you just add water to get a greater volume. So by definition, a dilution does not involve a change in the quantity of the solute. The moles of solute before the dilution is the same as the moles of solute after the dilution. All you're doing is taking whatever number of moles of solute this is, and you're adding water or solvent, if it's a different solvent other than water. You're adding the solvent and you're diluting it so the color gets lighter, the concentration goes down, you have less amount per given amount of space. So since the moles is not changing, if we think about what molarity is moles of solute per liter. If the moles is not changing, that's a constant. I can multiply both sides by liters. That will cancel. And I get volume in liters times concentration in molarity equals a constant. So this is only for dilution, only when the moles of solute is not changing. So that means if I have a certain volume at a certain molarity, that's equal to a constant. It should also be equal to a new volume with a new molarity. And that's my dilution formula. So this formula is very useful, but it's only for dilutions. You can use it for any problem that involves a dilution. So if the problem says there's a dilution happening, that's the formula for you. If it says that, it might not outright say a dilution is happening, it might say you have a certain solution, you're just adding solvent. Or you take a part of that solution out and you add solvent. That means it's being diluted with more solvent. Okay? So a dilution is a situation where you would use this formula. So here we say a student needs specific volume to have a certain concentration. They want to make that volume and that concentration by taking a more concentrated sample. So if you have a more concentrated sample and you want to make it less concentrated, you want the molarity to go down, you just add solvent. You just add water if it's aqueous. And that's what a dilution is. So you can use this formula. So the student is starting with this volume, they're starting with this molarity, and they want to end with this molarity. So you've got 3 out of 4 of the variables in this formula. You just plug them in. Plug in the volume, the initial volume, plug in the initial molarity, plug in the final molarity, and you can solve for the other variable. And so that's what you would be doing here in these dilution examples. So in this particular, actually I read that a little bit wrong. This is, let me switch around what I just said a little bit. I misread the question. The question says the student wants to make this final volume and concentration. So this is V2 and molarity 2. And this is the initial molarity. So we're plugging in the initial molarity, the final volume, and the final molarity. And we want to figure out how much of that initial concentrated solution do we need to start with, so that when we add enough water, it will get us up to the 250 milliliter. So that's what we're solving for here, the initial volume. And so once I plug everything in, I just need to divide by 2 molarity on both sides. The molarities will cancel. The 2's and molarities will cancel on that side. So I'll have the initial volume calculated by plugging that into my calculator. Any questions about that? because volumes in the lab are usually measured in milliliters, not liters, it's worth noting that this formula can also be expressed as molarity per times milliliters equals molarity times milliliters, instead of the initial molarity times the initial liters equals the final molarity times the final liters. I could use milliliters instead of liters. Really, I can use any volume. As long as, really ultimately this formula comes down to molarity times any volume equals molarity 2 times the new volume. As long as these two volumes have the same units as one another, it doesn't matter what volume units I use. And really ultimately, as long as these molarity units have the same units as one another, it doesn't matter what concentration units. I could use millimolarity or centimolarity or micromolarity. So really, a more general form is concentration 1 times volume 1 equals concentration 2 times volume 2. That's usually the formula that I use, because I know if I have two concentrations, as long as they're the same units, I can work with any concentration unit I want. And as long as the volumes are the same units, I can work with any volume unit I want. Here's another example. Here we have 12 molar HCl, which is usually, if you're going to buy HCl, that's the concentration it comes in. We want to know how much of that solution I need if I want the HCl to be more dilute at a lower concentration. So it doesn't say more dilute, but when I see that I'm going from a high concentration to a low concentration, usually that means that I'm adding just water to dilute it down to a lower concentration. So I would use the formula. I want to know what volume of this initial concentration do I need. So I'm solving for V1. The initial concentration is 12.0 moles per liter. The final concentration I want is 0.125 moles per liter. And the final volume I want is 150 milliliters. So I just divide both sides by 12. That will all cancel. The initial volume I need, the molarities cancel. It's going to be 0.125 divided by 12 times 150, 1.56 milliliters. Right, everything canceled except the milliliter, so that's the unit I'm left with. Questions about that? Another example. The square bracket notation should get familiar with. That's used a lot. The square bracket notation, if you see a number in here, or actually usually you'd see a substance in here. So if I say like AlCl3, the square bracket notation means if I have a number here, this means molarity. So that's moles of AlCl3 per liter of solution. So if you have the square brackets around the identity of a substance, and then that's equal to a number, the units are implied to be molarity, even if it's not outright telling you that it's molarity. So if I make a solution that's 1.02 molar aluminum chloride, what's the chloride ion concentration in that solution? Well, if I start with the AlCl3, this is ionic. So when I dissolve an ionic substance, what happens to the ions? Put this in water. As a solid, what's holding the solid together? Well, it's the attractions between the opposite charges. So as long as those attractions maintain and the atoms are held in place by those attractions, it's not going to dissolve. It'll still be a solid. The question is implying that it's dissolving, though, because it's giving me a molarity. That implies that I've dissolved a certain amount in a certain volume. So when it dissolves, that means that the ions have to separate from one another and be able to flow around. So that means when I separate the ions, because I'm starting with 3 chlorides, I have to have 3 Cl minuses for every one of these forming. So if I've started with 0.02 moles of AlCl3 per liter of solution, and I want to know how many moles of Cl minus do I have per liter of solution, I need a conversion. The units I have are moles per liter. The units I want are moles per liter. But it's not the same thing if it's not the same substance. Right? This is why it's critical when you do these conversions to write down not just the unit you have, but what substance that unit is referring to. Because the balanced reaction, as we talked about earlier, tells me the relationship between moles of one substance and moles of another substance. So if I want to get rid of AlCl3 because I'm interested in the chloride, I've got to cancel the moles of AlCl3 and get a relationship with the moles of chloride. And that comes from the balanced equation up here. 1 aluminum chloride gives me 3 chlorides. So now this cancels. And so I multiply that by 3 and I would get 3.06 molarity, or moles of chloride ion per liter of solution. Questions about that? We'll just do one more here because these three are exactly the same. So let's look at maybe part C. So in the Na2CO3, when this dissolves in solution as a solid, the ions separate, but the covalent bonds do not break. I'm just dissolving something. I'm not rearranging how the electrons are arranged. So this is not a chemical reaction. It's just dissolving. Okay, so when I dissolve molecules, the molecules stay intact. They just separate from their neighboring molecules and go off and get surrounded by solvent. So when I have a group of nonmetals, they're going to stick together. They need to stick together to maintain their noble gas configuration. So when I put that in water, the charges will separate because the water molecules are polar. They can bring their partial charges in and surround those charges and stabilize the charges so the charges can separate. But the covalent bonds can't break without making it really unstable. So I'll make sodium ions and CO3 2 minus ions. So to keep it balanced, I need 2 sodiums for every, since I have 2 in this formula. So then if I want to know how many moles of sodium ions do I have per liter, and I'm starting with, oh wait, that's not exactly the question. The question is asking me what's the molarity of this substance, so how many moles of Na2CO3 do I have per liter of solution if the solution has in it 0.124 moles of sodium ions per liter of solution. So the unit on the bottom is already what I want. I don't have to do any changes or conversions with that. What I need to change is moles of sodium into moles of Na2CO3. Right? So again, the relationship between one substance and another substance comes from their coefficients in the balanced reaction. So it's not really a chemical reaction, but in this dissolving process, 2 moles of Na plus are created for every 1 mole of Na2CO3. And so this will cancel. And so I'll have to divide that by 2, which will give me 0.062 moles of Na2CO3 per liter of solution.